beep for the big exam that's going to be tomorrow for chemistry honors periods 3 and 4. And I'm going to start with the lecture-y type comment or concepts first. So like things that probably won't involve too many questions. And sorry for the pause, I had to make sure everything was working, but now it is, so let's just get right into it. So first we're going to start with water. A lot of this stuff, by the way, was from 8th grade science, so you can remember it from there, but we're just going to go with like a brief review. So water consists of 2 hydrogen molecules and 1 oxygen molecule, or atoms, sorry. 2 hydrogen atoms and 1 oxygen atom. And the ears of this Mickey Mouse-like molecule are slightly positive, while the chin is slightly negative. And because of this, water is the universal solvent, meaning that it can dissolve polar and ionic compounds known as salts. And another effect caused by these slight charges on either sides are hydrogen bonds. So it's basically the hydrogen of one water molecule is attracted to the oxygen of the other. So this slight attraction between water molecules causes cohesion and adhesion. Cohesion is when water sticks to other things, or to itself, I'm sorry. Cohesion is when water sticks to itself, and adhesion is when water sticks to other things. And these hydrogen bonds are also responsible for surface tension, that the water molecules on the surface of a quantity of water are slightly drawn together, and that's why you can rest things like bugs and staples on it. And some more characteristics of water is that water is the only substance whose solid is less dense than its liquid form. So because our planet is covered with water, it's a really good thing that the oceans don't freeze over. Otherwise, fish would not survive, but ice just floats and things can survive underneath it. It also has high heat capacity, meaning that it can absorb a large amount of heat. It's a temperature regulator, and that also helps the surface of the earth have a good, reasonable temperature. So that's it for water. Also study up on metropolitan water district history. That's included in the chip. So now we're going to go to solutions. And a lot of this is also in Science 8, like it was covered in Science 8, like I previously stated. But a solution is basically a homogeneous mixture. And as you saw in the reading, if you read it, there's a small section in the chemistry textbook, and I really recommend reading that if you don't know about homogeneous mixtures. So a solute is the smaller part, and the solvent is the bigger part. And an example of smaller / bigger is when you put salt in a large glass of water, the salt would be the solute, solvent would be the water. And they sound pretty similar, so I personally remember it by counting the letters in this word. Solute only has 6 letters, solvent has 7. So since it has less letters, it's smaller. That's just a trick I use to remember. And there's 2 types of solutions, saturated and unsaturated. So saturated solution cannot accept any more solvent, while unsaturated solution can. And generally there's lots of different types of solutions. So you could do gas and gas, gas and liquid, solid and liquid even. And it doesn't have to be just gas and liquid or solid and liquid like we're all accustomed to. Like gas and gas solution, the example that we went over in class was air. It has about 20% oxygen and 80% nitrogen. Another example that I looked up just for fun was the air, or gas rather, inside of a scuba tank. It actually has oxygen and helium, for example. And there's obviously soda, which has sugar solute and the carbon dioxide solute. And right now I'm going to check the chat to see how things are going, so just excuse a small pause. And thank you for bearing with me. I'm not exactly the most technical person, so this is what I could get up and running in the short amount of time. But thank you for that. And okay, so on with this review. So another part of the chapter that is more memorization rather than a process is the DO, dissolved oxygen, TDS, and turbidity. So in any solution, not just water, not just lake water like we saw in class, increasing temperature and decreasing pressure decreases solubility. So what that means basically is if you have, let's say, a gallon of lake water and it has some dissolved oxygen in it from turbulence, which is just the water moving around, sloshing around as it does, and plants that live in the lake. So you already have some oxygen dissolved in there, but if you heat it up, then its solubility decreases. So what solubility basically is the ability for this solution to hold solvent. So you decrease it by heating it up, for example, which means the dissolved oxygen that is in the lake water will escape and it just won't have as much oxygen in it. And decreasing pressure, as we saw when you open a bottle of soda, it decreases the pressure and you hear the fizz. So it's the gas that's escaping from the soda because you allowed the pressure to decrease. And an important thing to note is when you have increasing temperature, it decreases solubility, and decreasing temperature increases solubility. But in the factory and fish example that we did in class, simply decreasing temperature doesn't return the dissolved oxygen into the solution. It just returns the ability for oxygen to be put back in. It doesn't necessarily mean that the oxygen levels are the same as they were before you increase the temperature. So this is dangerous for fish and other aquatic life near factories that use the bodies of water around them to cool their instruments and such, because when you dump heated water back in, it doesn't have enough oxygen that the fish need to survive. And fish and other cold-blooded creatures have their metabolism increasing as well if they're in a more higher temperature environment. So this it's called the double-edged sword. So just know that. Now we're moving on to TDS, which is total dissolved substances such as salts. And an important thing to remember, I just I just used to be confused, but TDS being high doesn't necessarily mean a bad thing, because you can have natural substances dissolved in the water that aren't necessarily unhealthy. So a river that starts with snowmelt, as it runs over the land, it's going to pick up things and have a higher TDS. And there is obviously the man-made TDS, like an oil spill, which is definitely harmful to you. And so you could test this with a conductivity test by putting in a circuit, and instead of clipping the alligator wires, you can allow the water to carry the current and see if it will carry the current. And or you could just simply let it out, leave it out, and allow the water to evaporate, and it'll leave behind the salt. And I'm going to check the chat right now. Okay, so we have a question from Sarah Rive. Thank you, Sarah. Is increasing or decreasing temperature changing solubility only for oxygen or all solutes? Increasing or decreasing temperature would change solubility. That's it. Oxygen in seawater is just one example, but I'm sure there's other like this. Increasing or decreasing temperature is a general rule, while oxygen and in seawater is an example of that rule. So I would say that it's not only for oxygen, it is for all solutes, to answer your question. So to continue, we have turbidity. And this is the clarity of the water in a sense. It's the amount of particles that are visible, so they do affect clarity, but they're too small to settle at the bottom, so they just kind of float around. The way I think of it is if you're in a sunny room and you see those little really tiny dust specks flying around in the air that are lit up by the sun, but you can't really touch them, like when you try to catch them, it really works. So that's how I think of these small particles, that they're just suspended. They're really small, so they can't sink. But a water clarifier that will coagulate the particles can be used to decrease turbidity, like in a pool. So basically it just works by drawing the particles together so that they become heavier and they sink, and they can just be simply cleared out physically. So that's that. And I am scrolling to the wrong place. And we are going to go do some names to formulas. Okay. So the main big idea to converting names to formulas, or formulas to names, either way, is you have to make sure that the charge equals 0. And you do this by, you can either look at the periodic table and figure out what charge it is based on which column it is in. And certain elements described on the chip that Mr. Bender gave us, they may have more than one charge, such as chromium, copper, iron, etc. So you have to really figure out based on context. But it's pretty easy to do that if you have another compound. You can kind of solve for the charges. And while zinc and Ni are in this metal area where you can't determine the charges, you just have to memorize that their charges are always 2+. Okay, so we have some examples here. So we have iron sulfide. So iron is one of those elements that we can't determine the charge of just with the periodic table because it's in the middle right here. So what we're going to have to do is first find the charge of these sulfur atoms by themselves. So there's 3 of them. Go over to periodic table here. So we know that one sulfur atom is +2. So then, or -2, I am so sorry. Nonmetals have a negative charge. So this one sulfur ion atom is -2. So all of this would be, and I just realized that you can't see that, would be negative, why isn't this working? -6. Okay, so that's for sulfur right there. So then we know we have 2 iron atoms that will have to total up to be +6. Because this is in a compound together, the charges of this and the charges of this have to add up to equal 0. So we know that all of the iron is +6. And you just do some basic division to find that each iron atom will have to have a charge of +3. And with these types of elements that you don't know the charge of, you will have to represent the charge in a Roman numeral. And so you have iron that each atom has a charge of +3, and then you have sulfide. Okay. Stretch that out. Okay, so now go to lead acetate, and lead is another one that has more than one possible charge, but we know that one acetate is -1, so you have 2 acetates here, which means that all of this has -2. So then one of these has to equal positive. I don't know why Google Drawing doesn't like straight lines, but one of these will have to equal +2. So that's pretty simple. Lead to acetate. Okay, so now we're doing names to formulas. So we have copper, which is +2 nitrate. So then Cu, and nitrate has a charge of -1. So in order to counteract, in a sense, +2 with nitrate, we're going to have to do 2 nitrates. Get the subscript. There we go. So then now we have chromium 3 oxide. And we're going to do that with, so we know that 1 chromium is 3. And then oxide, we could just see here, is -2. So this is one of the ones where you're going to have to add a number to both, because you're going to have to multiply, you're going to have 2 chromiums and 3 oxides for it to have +6 and then -6. So you're just going to do 2 of those and 3 of those. So that's how you balance the charges like that. The important thing is just to know, and I just forgot that I miswrote this. The important thing is to know that each substance, in a sense, will counteract the charges of the other. So the whole compound, in a sense, won't have a charge. So now I'm going to check the chat again. And it seems like questions have been answered. Okay. And to make a correction, for salts specifically, in the changes in temperature go along with changes in solubility. Different substances like cocoa powder, as Emma the Great has mentioned, will be affected differently by different temperatures. But the general thing is to know that temperature does affect solubility, and dissolved oxygen is an example of that. Gas in soda is an example of that. So just know that, and I will address the question. So there was a question that, do the middle elements all have multiple charges? So here, for the non-middle elements, you can determine, so this column, this column, this column, and then all of these, you can determine where they are based on the column. But these, however, you cannot. So you have to use context for these elements, or memorize just for these 2 elements. So yeah, definitely for the inside, the important thing is you're going to have to use the context, not a periodic table, to determine the charge. Checking the chat yet again. Okay, so I think that's that. Now we're going to go on. Why is that there? Okay. Okay, now we're going to go on to predicting precipitates. Now, the important thing is the precipitate rules that Mr. Bender has given us are pretty self-explanatory, but the way they work basically is that you have to first check if they apply to the first box. So what is soluble? So sodium and family, which is everything else in the same column as sodium in the periodic table, ammonium, nitrates, acetates, and it's all listed on the chip. And if none of these categories apply to the compound in question, then you look at what is insoluble. So that's why it says other carbonates, other phosphates, other sulfides. So if it's sodium carbonate, it is soluble, because the first thing you look at is that if one of the compounds is listed as soluble. But if nothing in the what is soluble box applies to the compound, that's when you look at what is insoluble. And of course there's exceptions, but that's pretty self-explanatory. They just don't follow the rules of the box that they are in. So, and you have to first check the products and then apply them to the solubility rules. So, aluminum nitrate and potassium hydroxide. What's going to happen is basically a switch. And so this positive is going to go with this negative. That's a janky arrow, but that's okay. And this positive is going to go with this negative. So what you're going to end up getting is aluminum with hydroxide. So if we check the what is soluble, it doesn't say anything about aluminum. But so we go on to what is insoluble because it counts as an other. So aluminum hydroxide is a precipitate because it is not soluble in water. So at the end of this reaction, basically, aluminum hydroxide will not dissolve. So it will be a solid, which is considered a precipitate. So aluminum hydroxide. And this was on the beep. It's just, and we can look at potassium nitrate. Well, we just saw it when the what is soluble that it's a nitrate. So that's soluble. So it's not a precipitate. Next example, sodium carbonate with iron 3 chloride. This is from the Sorcerer's Stone lab. So we have sodium, big red flag, because we know that sodium with anything is going to be soluble. So sodium chloride is soluble, not considered a precipitate. Then we have iron carbonate. So iron wasn't listed. Okay, that's a bad arrow. We'll try again. Okay, that wasn't much better. But anyways, iron carbonate. Let's see. Iron isn't listed anywhere in what is soluble, so then we go to what is insoluble. Carbonate is insoluble, so the precipitate will be iron carbonate. And that's great. So, last but certainly not least, it's sig figs, you know, all of our favorite. So, the important thing is to remember that you do your calculations as normal, and the whole sig fig concept is only coming into play when you have your final answer and you just need to round it. So after you get your final answer, you have to look at what's the most recent operation that you did. So if the most recent operation was addition or subtraction, you look at the place value of the least accurate measurement. And this is different than sig figs because you have to look at the place value rather than simply just the number of significant figures. So you actually have to pay a bit more attention to the place value. So if it's not addition and subtraction, if the most recent operation you did was multiplication or division, final answer has the same number of sig figs as the least accurate measurement, or the lame. So the hard part, generally people get that if it's a numeral, it's a sig fig, but it's when you get into zeros that it gets a little hairy. So the way Mr. Bender told us to think about it was that all zeros are considered sig figs unless they are just placeholder zeros. So what a placeholder zero is basically this zero is not giving us any information about the actual measurement. So it's only giving us information about the relative size, that it's just there to make sure we don't confuse it. We don't confuse 0.045 for 0.45. It doesn't give us any more information. So with considering zeros as sig figs, you might find it beneficial to look up additional rules that were not taught in class, because there are rules in the book. If you like to memorize or just have everything fleshed out instead of open to interpretation, I would definitely recommend checking the textbook or looking up rules, and that will just help you if you're more inclined to that method. So we're just going to go do some more examples. So we have 456.6, pretty self-explanatory. 4 sig figs. We have to the 10th, 4 sig figs, everything's great. Here, 456, 3 sig figs. It's pretty self-explanatory. We have hundreds, tens, ones. They're all giving us information about how large this object is, the measurement of this object. Now, we have 450, and even though there's 3 numbers here, it's only 2 sig figs. And the reason this is because this 0 here does not really give us any additional information. We don't know if this 0 is just there, if they just rounded to the nearest 10, or if it actually means something. So it doesn't mean anything. So it's only 2 sig figs. Now we're going to do some addition. You don't have to break out your calculators for this part. The important thing is that you get numbers of, or how many sig figs you will include in your answer, or how you will round your next answer. So you have an addition problem over here. So if this is, so addition and subtraction, you look at the place value instead of just the number of sig figs. So here we have very accurate, very accurate, very accurate. The least accurate, let's see, is to the 10th place. So whatever your final answer is, it's going to be rounded to the 10th place because this is the least accurate number. Least accurate. Only to the 10th place. Everything else goes on beyond the 10th place. But this stops there. So you're going to have to stop with it too. Now we go to multiplication. The rules are a bit different. Instead of looking at place value, look at number of sig figs. So you have this. This is multiplication, by the way. Sorry if it's confusing. So you have 4 sig figs here. Pretty self-explanatory. 5 sig figs, only 1 sig fig. So whatever the actual calculation you get, it can only have 1 sig fig because this only has 1 sig fig, and it's the number with the least amount of sig figs. So and then you might be saying like, oh wow, there's 3 numbers here. How is that 1 sig fig? It's because these zeros are only placeholder zeros. They don't give us any additional information about what the actual measurement is. So the only sig fig here is 3, which corresponds with this very nicely. So that was my stream. Thank you everybody for watching, and I will check the questions one last time to address any last questions. Okay, so we have Sarah Rive. Love you, Sarah. For precipitates, can you quiz us by giving us 2 compounds and asking if they would precipitate? Okay, I can do that. Art tablet, okay. Okay, so what has been proposed is an interaction with the chat, and I will definitely do that. So, let's see. Just give me 1 second to get some examples out. Okay, so these are from the Sorcerer's Stone lab. Also, I would recommend being familiar with these compounds just because they were in the lab and that's what we went over. So, and also for the fill in the blanks portion of the test, I would recommend looking at past MEs and PHs. Those definitely help, and he really explicitly said to me, Mr. Bender said to me in class today that he doesn't really draw from the chips, he draws from past MEs, which in a way are drawn from the chips, but really focus on MEs and PHs. So I'm going to ask, let's just make a new text box here. So we have iron chloride, oops, and oh no, wait, and copper sulfate. Will this precipitate? And we'll check the chat. And in the meantime, I'm going to answer another question. Okay, so the thing with the 300, or would we do it in scientific notation, even if the 300 only has one sig fig? Right, so the way Mr. Bender talked to us about scientific notation is basically it helps you get rid of zeros that you're not sure about necessarily. So, for example, zeros, I'll just use a space here. A zero, like this, these three zeros aren't significant, right? Because this only tells us about how small this number is. But these zeros are significant. And this is another example of the outside help if you want to look up rules regarding zeros and sig figs. Zeros between two significant figures are automatically significant. But really, the scientific notation would take out these because they're not significant, but it wouldn't take out these. So it kind of helps with that. And it also lets you know in your final answer if you're intending something to be a certain amount of sig fig. So that's really what I took away from that scientific notation. So, rap for us. Okay, I'm not a rapper though, but maybe if you score well on the test, I'll rap for you. Anyways, it doesn't seem like there are any answers here. Iron sulfate. What about iron sulfates? Is it soluble or is it a precipitate? Okay, so Matthew Lacayo, in his infinite wisdom, has said that iron sulfate will be a precipitate, and he is, I will begrudgingly admit that he is correct. So, iron sulfate wow, I knew I shouldn't have admitted that he's correct because he is incorrect. Iron sulfate will not precipitate. Thank you, Matthew. We know this because we look at the what is soluble, and number 5, it says most sulfates. And iron isn't listed as an exception. So we don't even have to look. I spelled this wrong. We don't even have to look at whether or not it's iron. It's sulfate, and iron isn't an exception. So iron sulfate is soluble. It will not precipitate. Thank you, Matthew. Okay, so I think that's that, and definitely more practice problems are definitely available online or in the book, and there will probably be better examples than what I could provide right now. So I think I'm gonna call it a day, and I will take any last questions. But if you'd like to spend a little time on feedback, that'd be great. This is my first time doing this, so any feedback, constructive feedback preferably, would be appreciated. So with that, I'm going to end the stream very soon. So any last questions? Okay, so the questions that I have been seeing, like a couple of serious questions. I will not rap. I'm not a rapper, though. So the significance of new baby buggy. Well, in class, he showed us a video of someone on Jeopardy that surprisingly guessed new baby buggy, which no one would have ever guessed. Okay, maybe next time list the solubility rules. Definitely I will do that next time. And I will have more graphics and other additional information next time, but this was oh yes, do you have a good way to remember solubility rules? So the first three listed there in soluble, what is soluble, is Na, so sodium, which is Na, ammonium, nitrates, and acetates. So that's na, or two Nas, rather. And really, there's only 4 more rules you have to memorize. I just memorize it the way I memorize everything else. And I don't have any clever ways to memorize it, sorry. But maybe try making something like never have fear of ice cold bears. That might work. And you could turn it in for some report credits. But and I've just been informed that it in fact is 3 Nas because Na, which is sodium, and ammonium is considered Na because it is NH4. So I am going to wrap this up. So thank you all for watching, and I hope that you really have good success tomorrow. Godspeed, everybody who's taking the test. So goodbye.